All right, guys. Yeah, so actually we are done with the section 7.1 and 7.2. So today, so we start section. So I'm gonna jump to the chapter 8. So we're gonna do section 8.1, the Green's theorem, and then after Green's theorem, I will back to the chapter 7. Okay, so today is so it's section. So this is section 8.1. So Green's theorem. And again, guys, I mean, if you have any question, please interrupt me anytime, right? Okay, so what's the Green's theorem? So what's the idea of Green's theorem? Well, so the Green's theorem, the goal of Green's theorem is the following. So the goal is, so the Green's theorem actually relates, well, before the goal, let me just remind you. So far, we have seen, so we have, first we have the double integrals, right? That's the integrals over regions in the plane, right? Double integrals. So that's so we integrate over regions, you know, in the plane. So we have two variables, x and y. Okay, so we also have, of course, the triple integrals. So triple integrals. So we integrate over solids in the space. Right? And then in section 7.1 and 7.2, we had line integrals. Okay, so in the line integrals, guys, so we had actually two different kind of line integrals, right? We have this scalar, you know, the scalar line integral, right? And we have the vector line integral. Okay. Well, so the Green's theorem actually relates, you know, a line, the vector line integral. So this one here, the vector line integral, okay, around some curve in the plane, okay, to a double integral over some region in the plane here. So this is, so it relates this vector line integral to this double integral here. Right. Okay, so the line integrals, guys, remember, so we integrate, of course, along a curve, right? This is, so here we integrate along a curve in the space or in the plane, right? Along a curve. And so what I'm saying is that, so Green's theorem so relates the vector line integral along some curve, all right, or around, let's say, a closed, and I will define in a couple of minutes what I mean by closed. So a closed curve or path in the plane. So we have some curve or path in the plane to a double, to a double integral over some region D, right? Over some region. Okay, some region in the plane. All right. So again, the idea behind this, Green's theorem, it gives a connection. So there is a connection, between vector line integrals. Okay, some vector line integrals along curves in the plane. So they have some connection with double integrals over some regions. Okay. So now, first, I'm going to define. So this Green's theorem actually involves what we call closed curves. Okay, so I'm going to define in a couple of minutes the closed curves. So the question now. So before Green's theorem, I have to define. So I'm going to define first what I mean by closed curve or path. So first question is. So what's a closed curve or path? Okay. Well, the definition is actually kind of very simple. So a path or curve gamma. So gamma, remember guys, definition of a path or a curve, it's some function from some interval AB in, let's say, R2 or R3, let's say it's Rn. So a path is closed if gamma of A is equal to gamma of B. Okay. So in other words, so you have your interval AB. This is your interval AB. This is AB. So let's say I have this curve in the space in R3. Okay. So my curve is this function from, this is my gamma. So it's a function from this interval AB in the space, right? So let's say gamma of A is somewhere here. This is gamma of A, all right? And then, here's some X in the interval AB. So somewhere you're gonna have, let's say here's the gamma of X, etc., right? And then what I'm saying is that gamma of A has to be equal to gamma of B. So which means that gamma of A and gamma of B, they coincide, right? So they are equal, so they coincide, they are the same point. So so my curve would be like, so I'm gonna just come back to gamma of A, because so gamma of A is equal to gamma of B, right? This is my A, here's my B, and gamma of A and gamma of B, they are just the same point. Okay, so that's a closed curve. That's what I call a closed curve, right? So it's just that the image of the endpoints of my interval, they coincide, they are equal. Okay, so it's closed. All right. Now, well, this is this example is very simple, basic example. You could have like more, let's say, more complicated closed curves. So for example, you could have an example where, so another example would be, let's say this is so this is like, so this is, let's say, gamma of A, and then you graph your path. So here's my path, right? And then of course gamma of A and gamma of B, they are equal, so you come back to the same point here. Okay. So what's the difference between these two curves, or these two paths? So in the first example here, this curve here, this one here, has no self intersection, right? It doesn't intersect itself, right? So here there's no self intersection. Okay, of course, except at at gamma of A and at gamma of B, because gamma of A has to be equal to gamma of B because it's closed, right? Well, now in this example here, this curve here, we have many self-intersections, right? So the curve intersects itself at many points, right? Like it intersects itself here, 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 etc. Right? So this curve here has many self-intersections. Okay, so here there are many self-intersections. Okay, so guys, what we're gonna do, we're gonna distinguish between curves with no self-intersections and curves with self-intersections. And actually, we're gonna call a closed curve with no self-intersection a simple curve. Okay, so so we say that the closed curve is simple a closed curve is simple if it has no self-intersections. If it has no self-intersections. Okay, except of course, gamma of A equal to gamma of B, right? That's the only self-intersection in a simple closed curve. Okay, so that's when the gamma of A is equal to gamma of B. Okay. So does it make sense to you guys? Why I mean by a simple closed curve, right? So it's closed, which means the endpoints, they have the same image, right? And it's simple, it means that it has no self-intersection, except of course at the endpoints, the gamma of A, which is equal to gamma of B, right? So I mean, here's more examples. Okay, so let's say you have this curve here. Let's say you have this curve, right? So this curve is, in this case, it's closed. Obviously, it's closed, and it's also simple, right? It has no self-intersection except, let's say this is gamma of A here, and that will be equal to gamma of B. Okay, so this curve would be closed and simple, right? Now let's take another example of curve. So let's say you have this one here, this curve. Okay, so this one here, this is gamma of A, gamma of B. Okay, so my question for you guys is this curve closed? Well, I mean, gamma of A is different from gamma of B. It's not the same point, so it's not closed, right? So this one here, so this curve here is not closed. Okay. Well, a third example would be, for example, let's say you have this one curve. So you have this one here. Okay, and I say here's my gamma of A, which is equal to gamma of B. Okay. And well, in this case, gamma of A coincides with gamma of B, so then it's closed. So this curve here is closed. And is it simple? Obviously, it's not, right? Because it has self-intersections here, here, and here, right? So it's not simple. Okay. Anyway, so is there any question, guys, about the closed simple curves? So why I'm introducing closed simple curves? Because that's what we use in the Green's theorem. I'm going to use closed and simple curves. Okay. Now, another important remark about closed and simple curves is that they have actually, in general, they have two possible directions or two possible orientations, right? So, for example, I'm going to take a numerical example. So, example number 4. So, let's say I have this curve gamma from 0 to pi in R2. Okay, and let's say gamma of t is equal to 5 cosine of t, phi sine of t. Right. So with, let's say, t, so t is in the, of course, t is in the interval 0 to pi, right? So t is in the interval 0 to pi. Okay. So if you want to graph this curve or path gamma, well, I mean, you can see here from the equation of gamma, or from the expression of gamma. So this is like your x, and here's like your y. So if you do x squared, if you do like x squared over, so x squared would be, of course, 25 cosine squared, and you divide by 25, so there'll be just cosine squared, and you take y squared, that'll be 9 sine square, and you divide by 9, so then it's just cosine square plus sine square, so that will be equal to 1, right? So this is the equation of an ellipse, right? So all I'm saying here, guys, is that my curve gamma here is just an ellipse. Okay. So if you try to graph this ellipse, take x here, y here. So let's say here's 5 here. This is the here. Okay, -5 and -3. Anyway, so first, if you want to check if this gamma is closed. So let's see. So my question is gamma closed? Well, the answer is yes, because so here's my interval. This is like a here. This is like my b, right? So a is 0, my b is 2 pi, and so if you evaluate gamma of a, so that's gamma of 0, right? So my t is 0, so that's like 5 cosine of 0, 3 sine of 0, and so that will be equal to 5, 0, right? So gamma of a is 5, 0. So if you do now gamma of b is 2 pi, so that's gamma of 2 pi. So that's 5 cosine of 2 pi, phi sine of 2 pi. Well, again, cosine of 2 pi, of course, is 1, so that will be 5, and sine of 2 pi is 0. Right, so the conclusion here is that gamma of a is equal to gamma of b, so my curve gamma is closed. Right, so gamma of a is equal to gamma of b. So the answer, well, yes, so gamma is closed. Okay. Now, what about the orientation of this curve gamma? So again, what I'm saying is my curve gamma is, so it starts at 5, 0 here. So this is gamma of a, right? Now, so for example, if you do gamma of pi over 2. So if you do, let's say gamma of pi over 2, so that will be 5 cosine pi over 2, phi sine pi over 2, and that will be equal to, cosine pi over 2 is 0. So this is a 0 phi, right? So like when my time t is pi over 2, you get the point 0 phi. So we go from 5, 0 to 0 phi. So here's my direction or orientation, right? So this is this point here. This is gamma of pi over 2, gamma of a, which is gamma of 0, of course. Now, if you do gamma of pi, that will be negative 5, 0. So here's my negative 5, 0. So this is gamma of pi. And if you do gamma of phi pi over 2, that will be 0, negative phi. So this point here is gamma of phi pi over 2. And finally, gamma of b. B is 2 pi. It's the same as gamma of a. So we're going to come back to the point, initial point, which is 5, 0. So that will be equal to gamma of b, which is gamma of 2 pi. So this curve gamma is closed, and it's also simple, right? Because it has no self-intersection, right? So gamma is also simple. So gamma is also a simple curve. Okay. So what about the orientation here of gamma? So the orientation here, or the rotation here of this ellipse is, counterclockwise rotation, right? So the orientation of gamma is actually counterclockwise. Now, I can parameterize this ellipse, the same ellipse, with the different parameterization. So I can parameterize this using, for example, another parameterization. So let's say now I have alpha of t. So a different parameterization. So let's say you have alpha of t equal to 5 cosine of 2 times pi minus t. Okay, and then phi sine of 2 times pi minus t. Okay, with t in the interval 0 pi. Okay. So for example, if you do alpha of 0, well, it's, if you replace t by 0, that will be actually the point 5, 0. Okay, t is 0, then you're gonna have, for example, like 5 times cosine of 2 pi. Cosine of 2 pi is 1, so that's 5 times 1, so that's 5, right? And for sine, that'll be sine of 2 pi, that'll be 0, right? And if you do alpha of pi, same thing, pi minus pi, that'll be 0. Cosine of 0 is 1, so that's also, you're gonna get also the 0.50. Okay, so alpha of 0 is equal to alpha of pi. Okay, and anyway, so this, and the same thing here. If you take, the first component is supposed to be your x, right? This is your x coordinate, and the second component is your y coordinate, right? And the same thing, if you do x squared over 25 plus, if you do x squared over 25 plus y squared over 25, because you see, guys, you have the same, this is the same angle, right? Here's we have the same angle, right? So the cosine square of this 2 pi minus t plus the sine square of the 2 pi minus t, that will be equal to 1, right? Because we do have the same angle. So so again, what I'm saying is this alpha is also a parameterization of the same ellipse, right? So this is equal to 1. Okay, so my alpha is just the same ellipse. It's just a parameterization of my curve or path gamma, right? It's just the same ellipse. Now, what's the difference between gamma and alpha? So we are saying alpha and gamma, they represent the same curve, the same ellipse. Okay, it's the same ellipse. However, there is a difference between alpha and gamma. The difference is the orientation. So for example, here you have alpha of 0 is 5, 5, 0. But if you do, for example, next point, let's say pi over 4. If you do pi over 4, alpha of pi over 4, and if you evaluate alpha of pi over 4, that will be, I claim that that will be equal to actually 0, 0, -3. Okay. So what I claim, guys, is that, so if you want to graph your alpha, so alpha of 0 is this point here, right? Okay, but then alpha of pi over 4, it would be this point. Okay, so this is alpha of pi over 4, alpha of pi over 4. All right, and then if you do alpha of pi over 2, that will be the -5, 0. Alpha of 3 pi over 4 will be this point here. And finally, alpha of pi would be again the 5, 0. Okay, so the thing is, so the difference between alpha, they represent the same curve, but the orientation is they're opposite. Alpha has opposite orientation, right? So alpha goes in this, it has a clockwise orientation, or clockwise rotation, right? It goes from this point, you're gonna go there, you're gonna go here, and then you go here. Okay, so alpha has a clockwise rotation, right? And gamma, of course, it's counterclockwise. Okay, so the conclusion is that alpha has opposite direction to gamma, right? So conclusion is that alpha has opposite direction to gamma. Okay, so my point here, guys, is that, so my ellipse, as I said, this ellipse here, or this curve here, is it's actually a closed simple curve, right? But my point here is that a simple closed curve has two possible orientations. Okay, so remark, a simple closed curve has two possible, remark, so a simple closed curve or path has two possible orientations. Okay, and actually we say that a simple closed curve is oriented if a choice of orientation is made. So if you make a choice of orientation, if you say my curve or my path is or my ellipse has a clockwise orientation, it means that you oriented your curve, right? So we say that a curve, a simple closed curve is oriented if a choice of orientation is made. If you choose some orientation, then we say that the curve is oriented. Okay, is oriented if a choice of orientation is made. Okay. Again, we have this example of this ellipse, right? We have this alpha and gamma. They both represent the same curve. And we said this ellipse is actually a simple and closed curve, right? And then we said we have two possible orientations, right? We said the alpha has the opposite orientation to gamma, right? So this is like a general fact. Whenever you have like a simple closed curve, then you have always two possible orientations. Okay. Is there any question, guys, about the simple closed curves? All right. Okay, now we can actually state the Green's theorem. Okay, so let me now say what's the Green's theorem. Okay, so I'm gonna try, because there are some, I'm gonna use some terminology in this theorem. I will try to, explain the terminology at the same time, and then I will give you some examples. And you see, it's not that bad. I mean, the theorem is not, it's not really hard. I don't think it's really hard. And then we're gonna have some examples, exercise, and then I'm gonna try, there are different ways actually to formulate this Green's theorem. So I'm gonna start with a very simple formulation of this theorem, okay? And then later, at the end of the lecture, I'm gonna try to reformulate this Green's theorem, okay? So there are different ways to state this Green's theorem. Anyway, so I would say the first formulation is the following. So let's say you start with so we have some, so D be a closed bounded region in R2 in the plane in R2. Okay, and so it's some region in the plane and whose boundary okay, so you can imagine your D is just it's some, this is my D here, it's just some closed bounded region in the space. Okay, so this is my D here. Okay, so I have this region D, and the boundary of D, so such that the boundary of D, so whose boundary C, so the boundary of a region in the space, it's a curve, right? So if you take the boundary of this region, this is your boundary of the region, right? This is the boundary of your region D, right? So this is, here's the boundary of D. So if you have a region, let's say a closed bounded region in the plane, the boundary would be some curve, okay, or curves. So whose boundary C, and actually there is a notation for boundary. It's with this del here, so del of D. Okay, so this del means the boundary. This is just a notation for boundary. Okay. So whose boundary C? So the boundary of this region D, C, consists of finitely many simple closed curves. Okay, so so this boundary C, capital C, consists of finitely many simple closed curves. Okay. Okay. So, for example, so examples. Of course, I didn't finish Green's theorem. I'm trying to explain what do I mean by this, you know, having this region D with boundary C, consisting of finitely many simple closed curves, right? So, for example, let's say you have the annulus. So D is just okay. So this is your region D. So D in this case is the annulus. So what do I mean by the annulus? Is that's the region bounded by two circles, right? So then in this case, what will be the boundary of this annulus? Well, the boundary of this annulus would be, so we're gonna have two curves, not just one, right? So we're gonna have the first boundary is this one here, the first circle here. So this is, let's say, let's call this C1. That's the first boundary. And there's a second boundary, which is this one here. And that's another curve. Okay, so your boundary here, the boundary of this region D is actually the union of two curves, right? C1 and C2, right? You have these two curves. And of course, both C1 and C2 here, they're just circles. So they are just closed. They're closed, simple curves, right? So the boundary, so in this case, so C, which is the boundary of the region D, is actually the union of two circles. Okay, C1 and C2. So that's why here I'm saying that you know, the host boundary consists of finitely many simple closed curves, right? So like in this case, we have two, the boundary is actually consists of two simple closed curves, right? Another example would be, for example, if you take a triangle, so my region D would be, let's say, this one here. So this is my region D. Okay, so my D in this case is a triangle. Now, the boundary of my triangle, so we're gonna have, of course, there are three sides, right? So the first side here, let's call this side here C1. This is my first line segment. There's another segment here. This is a C2, and there is C3 here. Okay, so the boundary, so C, which is the boundary of D, is given by the union of these three segments here, right? C1, C2, C3. Okay, and of course, in this case, this boundary here, you know, this boundary here is a closed, simple curve, right? The union of C1 with C2 with and the C3 is a closed, simple curve, right? So this is, again, this is simple, closed curve. Okay. Why again here? I'm saying the boundary consists of finitely many simple closed curves, because you could have like D, your region D could be like a union of disks. So for example, last example here, let's say your D is not just one disk, but you're gonna have, let's say, 3 disks, like 1, 2, 3, 4. So my region D here is the union of these 3 disks, right? Okay, so D here is the union of the 3 disks. Okay, so what would be the boundary of D in this case? Well, so the first disk here, the boundary would be this circle, right? Second circle here, and the third circle here. So C1, C2, C3, right? So in this case, the boundary of D is just union of 3 circles. 3 circles. Okay. So anyway, in the statement of the theorem, we need C, the boundary of D, to be a finite number of simple closed curves. Okay, so this finitely many, it means that C is just a finite number of simple closed curves, right? Finite number. What do I mean by a finite number? I mean, it's not infinity. Okay, just a finite number. Anyway, so there is another requirement here in the Green's theorem. So we have this region D, whose boundary consists of finitely many simple closed curves, right? Now we're gonna give orientation to these curves, to this boundary. So we need to orient the curves of C so that. So now this is a continuation of Green's theorem. As I said here, guys, I just explained what do I mean by, region D whose boundary C, etc., consists of finitely many simple closed curves, right? Now, so I'm going to continue with the Green's theorem. So we need to give an orientation to this to the boundary. So we need to orient the curves of C, which is the boundary of D, so that D is on the left. So that D is on the left. Okay, as one traverse C, as one traverses C. Okay, so in these examples here, for example, the first example, I need to orient my boundary C so that D is on the left, okay, as one traverse C. So like for C1, I'm gonna orient C1 like this, because you see, guys, as one traverses C1, the D would be on the left, right? So if you give this orientation to C1, okay, D would be on the left of this arrow, right? Because, right, so D is on the left, D is here, right? It's on the left of here, this orientation, right? So here's my orientation. So it's a counterclockwise orientation here, because D would be on the left of my arrows, right? Okay. Now, What about the orientation of C2? So again, you need D to be on the left of the orientation, right? So now for C2, it's gonna be clockwise orientation, because so that D would be on the left of the arrow, right? So D would be on the left. So the right orientation for C2 is the clockwise orientation, right? Okay, so here D is on the left of the orientation of C1 and C2. Okay. Does it make sense to you guys? Why I choose the the counterclockwise orientation for C1 and the clockwise orientation for C2, right? So because in both cases you need D to be on the left, as you traverse the circle. Okay, so next example number 2. I'm gonna give an orientation to C1. Of course, there are 2 possible orientation for C1. I mean, you can go from here to here, or you can go from the other direction, right? Now, the question is, which one is the required by the Green's theorem? So, the one required by Green's theorem is the one says that the D would be on the left. So, like for C1, the right orientation would be this one here. Okay, so then the region D is on your left. The same here. You need D to be on the left, and here, D would be on my left, right? So, so D here is on the left of the chosen orientation, right? Orientation of C, the boundary. Okay. Now in the last example, well, like in the last example, we have these discs, right? So for C1, the right orientation would be this one here, the counterclockwise orientation, because D would be on the left of my orientation, right? So this would be the right orientation, the orientation that you need for Green's theorem. Okay. All right. So in this Green's theorem, so we have this region D bounded, or with the boundary C, which is a finite number of simple closed curves, right? And then you need a specific, or you need to orient the curves of the boundary of C so that D is on the left as one traverses C, right? All right. Now we were almost done with this Green's theorem. So now let's say you have, remember guys, the goal of this Green's theorem is to relate a vector line integral along some curve in the plane to a double integral, right? So vector line integral means we have some vector field, right? A force field. So let's say you have f of xy. So we are in the plane. So we're going to have just 2 variables here. We only need 2 variables. So this force field f is given by 2 functions. Let's say, so this is like the sort of the notation for this force field in case of Green's theorem. So let's say you have first function m of xy, and n of xy. Okay. B, so this capital F be a vector field. Throughout this region D. Okay, so again, m of xy, m and n are just functions. Okay, m xy and n of xy are just functions from R2 to R. Okay, now what does it say, the Green's theorem? So then the integral, or the vector line integral of f along the boundary. So the integral of this force field f along the boundary, along C, which is the boundary of D. Okay. So here we have, this is a scalar. This is the scalar product. They have a force field. The ds, that's the displacement vector. All right. So then this this vector line integral is going to be equal to the double integral. So you know, f is supposed to be equal to f of xy is supposed to be equal to these two functions, right? M of xy and n of xy. Okay, so in other words, we have this integral here, m of xy dx plus, you know, this is just another notation for this this vector line integral, right? So dx plus n of xy dy. Okay, this is just a notation for our vector field of vector line integral. Okay. So what does it say, the theorem? Well, it says that this vector line integral is equal to, and this is actually equal to the double integral over D. So the D, that's your region, right, in the plane. And the C here, this curve C here is the boundary of D, of your region, right? So the double integral over D of a derivative of the function n with respect to x minus the derivative of the function m with respect to y. Okay, dx dy. Guys, remember we said this this curve C here, which is the boundary of the region D, is supposed to be a finite number of closed simple curves, right? And so this is supposed to be closed simple curves, right? Now, guys, when you integrate along a closed curve, then actually there is a notation here in the integral. You're going to add like sort of a circle here. Okay, so this circle means that this is this symbol here, this one here. Okay, so the symbol here, this circle here, indicates that the integral is taken over along a closed curve. Okay, so this is symbol here indicates that the integral is along a closed curve. Okay. So again, guys, so this is the Green's theorem. So you have on one side, you have a vector line integral, right? You have this, this is my, you know, this is my vector line integral, okay, along this curve C, which is the boundary of some region D, right? And Green's theorem says that actually this vector line integral along this curve C, which is the boundary of D, is the double integral over D over the region itself, okay, of this difference between the partial derivatives, okay. So let's take an example. Okay, let's do an example. A numerical example. Okay, so let's say you have D is the region bounded by the line y equals to x and the parabola y equals to x squared. Okay, and let's say my force field F is equal to let's say xy y squared. Okay. So in the notation of Green's theorem, so this is like this is my function m, capital M. So this is my function m of xy, and this is my function n of xy. Okay. And let's say you want to verify. So the question here. So question is verify Green's theorem. So we're gonna check if Green's theorem is true or not. Of course, it's true, but we're gonna just check if it's true, if it's true, right? So in the Green's theorem, there are two sides of the equation, right? So we have this first. We have this, this vector line integral. All right, and then we have to compare it to this double integral over D. Okay, so first step one. So let's say in step one, so step one, I'm gonna evaluate the left side of Green's theorem. So I'm gonna evaluate this this vector line integral along the boundary of D. Okay. Okay, that's the left side of Green's theorem, right? And then in the step number two, I'm gonna evaluate the right side. Okay, the double integral. So let's evaluate the vector line integral. So, well, we know f. Okay, that's cool. Now we need to find this boundary, right? C, which is the boundary of this region D. So what's the region D? The region D is bounded by this y equals to x and the parabola. Where's my parabola? And the parabola y equals to x squared, right? So first thing to do here actually is, so we need to parameterize the boundary of D. So we need, so the missing information here is the parameterization. So we need to, so we need to parameterize. So this is known. That's cool. This is known. It's given here in the problem. Now, but the thing is, we need to parameterize this boundary. So we need to parameterize. C. Okay. So what's C? Well, so let's just I'm gonna sketch the region D. So probably gonna, here's 1, here's 1, here's 0. So we have the line y equals to x. All right, so here's the line y equals to x. I mean, it's supposed to be the diagonal. So this is, I mean, y equals to x. All right, and we have the parabola y equals to x squared. So of course, between 0 and 1, x squared is less than x. Right, it's like in the test. So if your x is between 0 and 1, when you take a power, I mean, if you're like x squared here, x squared would be less than x. So between 0 and 1. So x squared would be like it's less than x, but then of course after 1 it will be x squared will be larger than x. Okay, so this is x squared, y is equal to x squared, right in the side here. Anyway, so my region D, of course, is bounded by these two equations. So my region D, here's my region D. So this is my region D. Okay. So now, what's the boundary of the region D? Well, the boundary of this region D is it's this this segment, line segment here. All right, and this one here. So let's call this C1, and the parabola here. Let's call the parabola here. This part here. This portion here, C2. Okay. Now the boundary of D would be the union of C1 with the C2, right? The boundary of D is the union of C1. So the boundary of D, which is C. So C, which is the boundary of D, is the union of C1 with C2. Right. Again, C1 is this line segment here. Right, and here's C2. Okay. Anyway, so this boundary here, the boundary of D is, of course, it's closed and a simple curve, right? It's just you know, you have this curve here. This is closed and simple. Okay. So it verifies the assumptions in the hypothesis in Greer's theorem, because you need the boundary to be closed and simple, right? Now, what about the orientation? So you have this closed simple curve. So you need to orient this this curve such that your D would be on the left of your orientation, right? So so for C1, the orientation would be, so you want a D to be on the left, right? So for C1, the orientation would be, let's pick a blue, this blue here. So for C1, the orientation would be this one here, because you need D to be on your left. And for C2, the orientation would be the other side here. Okay. So first, you need to parameterize. Let's say you want to parameterize C1. So first, let's parameterize C1, and then I'm going to parameterize C2, and then I'm going to compute my vector line integral. So parameterize C1, but in C1 here, you have to be careful. Because careful with your orientation. Okay, so how do we parameterize C1? Well, C1 is just a portion or line segment in the line y equals to x, right? So it's a segment of line segment of y equals to x. But of course, it's not the whole line. It's just you know, it's from it joins the point 0, 0 to the point 1, 1, right? So your x or your y both actually are between 0 and 1, right? So your x here is between 0 and 1. Okay. Because it joins it connects 0, 0 to 1, 1. Okay, so the x coordinate, for example, is just from, it's between 0 and 1. The same for y, actually. Now, you may say, well, a possible parameterization of this would be, well, to say, for example, we can say x is equal to t. Okay, so if you say x is equal to t, then of course y, which is equal to x, would be equal to t, right? And so a parameterization would be, let's say, gamma of t equal to your x, which is t, and your y, which is also t, right? And because x is between 0 and 1, so then all t would be also between 0 and 1, because x is equal to t, right? But this is actually not the right, so this is not the right orientation required by the Green's theorem. Why? Well, because if you so t is in 0, 1, right? So if you do gamma of 0, that will be the origin, and if you do gamma of 1, that will be 1, 1, right? So we are moving from 0, 0 to 1, 1. But if you move from 0, 0 to 1, 1, that will be the opposite orientation required by Green's theorem, right? Because so if you move from 0, 0 to 1, 1, so that will give this orientation here. But that's the opposite orientation required by Green's theorem, right? So this orientation here this orientation is the opposite it's opposite to the orientation required by Green's theorem in Green's theorem. Okay, so actually you want to go from 1, 1 to 0, 0, not from 0, 0 to 1, 1, right? So the orientation required in Green's theorem is you have to go from you need to go from 0, 0. Sorry, you need to go from 1, 1. This is 1, 1 to 0, 0. Right. So this is not right parameterization. This is because it gives you the opposite orientation. Okay. So we need to go from, or you need to move from 1, 1 to 0, 0. To 0, 0, sorry. Okay. Now, actually, guys, in general, if you wanna have the opposite orientation, all you have to do is to take, instead of t, you have to take like 1 minus t. That will give you the opposite orientation. Okay, so to get the opposite orientation, because if you take 1 minus t, if t is 0, it gives you 1. And if t is 1, it gives you 0. So to get the opposite orientation, we need x to be equal to 1 minus t, and so y, which is equal to x, is also equal to 1 minus t. And the same thing here, and because your x is between 0 and 1, then if you say, well, x is 1 minus t, so that means 1 minus t is between 0 and 1. Okay, but 1 minus t is between 0 and 1. If you subtract subtract 1 and you solve for t, then t would be also from 0 and 1, between 0 and 1. Okay. So for this curve C1, the first curve, so again, we need to parameterize C1, right? That's the line segment. So that's the line y equals to x, right? From 1, 1 to 0, 0. So C1, right parameterization for C1 would be, let's say, gamma of t equals to 1 minus t, 1 minus t, with t between 0 and 1. Okay. So that's the parameterization for C1. Now, we need to parameterize C2, right? So we parameterize C1. We have to parameterize now C2. So parameterize C2. So what's C2? Well, C2 is so it's in the parabola y equals to x squared, right? So here's my C2, right? This is, oops. So here's my C2, right? This is this portion of this parabola, right? Y equals to x squared. And the orientation is, so you're moving from 0, 0 to 1, 1, and that's perfect, okay? So you're moving from 0, 0 to 1, 1. So y equals to x squared. Again, you want to parameterize this. You can say, for example, x is equal to t. So this is y equals to x squared from 0, 0 to 1, 1, right? Okay, so then let's say x is equal to t, then y, which is x squared, would be equal to t squared, right? Now, what will be the interval for t? Well, x is between 0 and 1, x is t, so then t is between 0 and 1. Okay. So you can take the following parameterization. So C2 is parameterized by by beta of t, which is equal. So x is t, y is t squared, with t between 0 and 1. Okay, and of course, if you check the orientation, beta of 0 is the origin, and beta of 1 is 1, 1. So we are moving from, from 0, 0 to 1, 1, and that's the correct orientation. That's the orientation required in the Green's theorem, right? So from 0, 0 to 1, 1, and that's exactly what we need. Okay, so that's the orientation required by Green's theorem. All right. So we are still trying to evaluate the first slide, in this Green's theorem. Again, guys, the first slide we said it's this integral, vector line integral along C, which is the boundary of D. We know D, right? But we have to parameterize the boundary. So that's what we are doing now. Once you parameterize the boundary, you know your force field, so then you are good to go. You can compute your vector line integral. So, okay, so I got parameterization of C1, parameterization of C2. So now we can compute. So now we can evaluate my vector line integral. Now we can evaluate okay, so this vector line integral along C, which is the boundary of D, is, so this boundary of D is the union of these two curves, right? The C1 and C2. So that will be equal to the vector line integral along C1 plus vector line integral along C2. Okay. So that would be equal to, so C1, that's it's parameterized by gamma of t, and C2 is parameterized by beta of t, right? So gamma of t, so this would be f of gamma of t, scalar product with gamma prime of t, dt. So t here on C1 is in the intervals 0, 1, and the same here for C2 is parameterized by beta of t. So that's, again, t is between 0 and 1. It's f of beta of t, scalar product with gamma prime of, not gamma prime, but beta prime, because my curve C2 is parameterized by this beta of t. So beta prime of t dt. All right, so then that would be equal to, so just to remind you guys here, let me write down here for you. So the f was equal to, let's see, what was f? F was equal, the force field, vector field, f was equal to, yeah, x, y, and y squared, sorry. So it's x, y, so it's x, y, and y squared. All right, gamma of t, that's the parameterization of C1. That's, we said it's 1 minus T1 minus T. And beta of t, we said is just t and t squared, right? Anyway, so for the first vector line integral here, so that will be from 0 to 1. So the vector force field F along gamma, so it's x times y. So here's x along gamma, here's y along gamma. So that's 1 minus t squared. So here's 1 minus t squared. Y squared, that will be also 1 minus t squared. Scalar product with gamma prime of t. Gamma prime of t, derivative with respect to t, it's minus 1 dt, right? Plus, now, beta along beta, so the vector field f along beta, so that will be, so beta along beta, x is equal to t and y is equal to t squared. So if you do x times y, that will be t times t squared, and right. So that will be equal to t times t squared, that's t cubed. And then you have y squared, that's t to the power 4. Scalar product with beta prime of t. So derivative of beta of t, that will be derivative of t is 1, derivative of 2t, t squared is 2t, dt. All right, and so that will be equal to, so the first scalar product, this one here. So 1 minus t squared times negative 1 plus 1 minus t squared times negative 1, that will be minus, negative minus, 1 minus t squared minus 1 minus t squared dt plus, and then you have this integral from 0 to 1, t cubed times 1. So that's t cubed, sorry, that will be t cubed here, plus 2t times t to the t4th, so that will be 2 times t to the power 5. So that's t to the power 5, dt. And actually, that's actually easy. It's not really hard to compute. So this is easy to compute, right? You can just integrate with respect to t, and then you evaluate from 0 to 1. And I think the answer would be the answer would be -1/12. So this is just the first side of the equation of the of the equality in the Green's theorem. That's the vector line integral along the boundary. So the hardest part, I would say, in this thing here is to parameterize. It's to parameterize the boundary. You know the region D, but then you have to find the parameterization of the boundary. Okay, and I mean, usually, most of the time, how do we parameterize the boundary? Well, for example, your boundary is a line or your parabola. It's given by some equation, right? Like, let's say y equals to x squared or y equals to x cubed or wherever. You can just say x is t, and then, because y would be equal to x squared, so then your y would be equal to t squared or y equal to t cubed or whatever, right? But then just be careful with your notation, because in that case, like here, if you say x is equal to t, and then your y is t squared or t, then you are moving from 0, 0 to 1, 1. Okay, so if you want to move in the opposite direction, my advice, or I mean, what I would recommend is to say, well, x is equal to 1 minus t. Okay, so 1 minus t would give you the opposite direction in general. Okay, of course, it depends on the curve, but that's usually how it works. Okay. But then, of course, then you have to evaluate this vector line integral. Once you have the parameterization of the boundary, I think it's not really hard to evaluate the vector line integral. So this is the left side of Green's theorem, right? So we have. Let me come back to this Green's theorem. So in the step one, we want to verify Green's theorem, right? So we had to evaluate this vector line integral along the boundary of D. So we had to parameterize the boundary of D. That's the main thing to do here in the first step. Now, the step number 2, I'm going to evaluate the right side of Green's theorem. So what's the right side of Green's theorem? It's just the double integral. So it's just this double integral over D. We know D. Of the derivative of n with respect to x minus the derivative of m with respect to y. So this is just a double integral. So let's evaluate this double integral, right, for our region D. Remember, D is this region here bounded by y equals to x and y equals to x squared, right? So we can find the bounds for D. So in step number 2, we're going to evaluate the double integral over D of partial m, partial, where is it? Partial n. Oops. Right, it's partial n here. It's partial n, partial x minus partial m, partial y. Right, dx dy. Anyway, what's n and m? Well, we said my vector field f of xy, that's the m of xy, n of xy, right? And in this problem, in this particular example, this force field f is just we said it's x times y and y squared. Okay, so here's my m. And here's my n, y squared, right? So then this is just a derivative of n with respect to x minus derivative of m with respect to y, right? Now, so what we have to do here in this problem, well, we have to find the bounds for D, right? Because we have this region, D, and it's not really, D is just to remind you that D is just a so we have this y equals to x, and we have this y equals to x squared, and x, this is 1 here, this is 1, 1, of course, this is 0, and this is 1 here. All right, so what will be the bounds for D? All right, this is just an elementary region, so we can I mean, you can find that. So this is, here's your D. It's an elementary region. You can say, for example, your X is between 0 and 1, right? So my X is between 0 and 1. Right? Because my X coordinate here. So this is like, here's my X equal to 0. And here's like my X equal to 1, right? So my X is between 0 and 1. So then my Y, so then Y would be between, once you fix X, Y is between, and the bottom here, this is X squared. And the top here, Y is equal to X. Okay, so then Y is between X squared and X. Okay, if you fix X, then Y is just between X squared and X. All right, so we can, so my double integral over D of derivative of n with respect to x minus derivative of y, derivative of m with respect to y, dx dy, this would be equal to, so I'm going to integrate first with respect to y and then with respect to x. So y is between x squared and x, and x is between 0 and 1. Now, what's the derivative of n with respect to x? Well, n is the y squared. Okay, so I'm gonna just write it here. So derivative with respect to x of n is the y squared, right? And the m is the x times y. So derivative with respect to x of y squared minus derivative with respect to y of m, and m is xy. Okay, so that will be equal to double integral from 0 to 1 x squared x, derivative with respect to x of y squared, of course, then y would be constant, that would be 0. And here, x is a constant, so derivative of xy with respect to y would be just the constant, which is x. So that would be just minus x. So this is just minus x dy dx. You integrate with respect to x, with respect to y. So that would be 0, 1. Derivative x is a constant with respect to y. So integral of constant would be the constant times y, evaluated between x squared and x dx. So now that will be equal to 0, 1 minus x. So 1y is x and minus 1y is x squared dx. So that will be equal to double integral. That will be x cubed plus x cubed minus x squared dx. So that's x fourth over 4 over 4 minus x cubed over 3 from 0 and 1. And this is 1/4 minus 1/3. And then minus x is 0. So it's going to be just 0, 1/4 minus 1/3. Common denominators will be 12. So that's 3 minus 4. That's negative 1 over 12. And that's exactly the answer we got on the left side. Right? This is negative 1 over 12. On the left side, we also got a negative 1 over 12 here. Okay. And so the conclusion is that, of course, as expected, so the conclusion, of course, is that this vector line integral along the boundary of D is equal to this double integral over D of partial n, partial x, partial minus partial m, partial y, dx dy. Okay, where f, of course, So both are equal to, of course, -1/12 in this example. Right? Okay, so we just verified Green's theorem, right? I mean, let me just before the exercise, guys, let me just say why this is kind of a very beautiful theorem, because in some sense you can calculate. So for example, let me show you one consequence of this Green's theorem, and you will see with this consequence why this Green's theorem is kind of really nice, because just a consequence of Green's theorem. So let's say you have some region D. D is a region in the plane, right? To which Green's theorem can be applied. Remember, we have all these hypotheses above the boundary. You need the boundary to be closed and simple, etc., right? So to which Green's theorem can be applied. And the thing is, so if you want to compute, for example, let's say take f of force field F equal to, let's say, minus y and x. Okay. So in some sense, so this is my m, and this is my n. All right. So if you take half of this of the vector line integral of this force field F minus y x, right? So that would be equal to actually half. Now, if you do derivative of n, this is my n with respect to x, right? So derivative with respect to x of x minus derivative with respect to y of m, but m is minus y, right? Dx dy. So then that will be equal to, so half, this is over d, of course, over d. Derivative of x with respect to x is just 1, minus derivative of y of minus y, that will be minus y, so it's -1, so it's going to be minus will be plus 1, so that's 1 plus 1, dx dy, so that will be 2 here, and times half, that will be 1, so this is just 1 dx dy over d, and this is the area of d, right? This is, so this thing here, this is by definition, this is the area of D. And so what we are saying here, using Green's theorem, you can calculate the area of a region. So the area of a region is like a two-dimensional notion, right? It's an area, right? It's a plane. So it's sort of a two-dimensional notion, right? You can calculate this area, which is a two-dimensional notion, by using line integrals. And line integrals are, so they are defined along a curve. So that's a one-dimensional. It's a one-dimensional notion, right? So this is a two-dimensional area of D. This is two-dimensional notion. And this vector line integral, well, it's called vector line. So a line, it's one-dimensional notion, right? Vector line integral, which is a one-dimensional. Okay. And this is kind of surprising, right? I mean, you are trying to compute some two-dimensional notion, and in fact, you can just use a one-dimensional, one-dimensional notion. right? So in some senses, like you don't really care what's going on inside your region. What's really important is what happens on along the boundary, right? Along the boundary of your region. Anyway, so we'll see in the reformulation of this Green's theorem, we'll see more like geometric interpretation of this Green's theorem. But before the reformulation, guys, I'm gonna give you a couple of exercises. Just the same as I did in the example. So where you have to verify Green's theorem. So I guess probably we won't have time to do, to solve all these problems today. But let me just write down the problems or exercises. And probably next time I would do probably one example. I want to go over one problem. And actually, in the homework, you'll find a couple of problems about this Green's theorem. It's again, it's just all you have to do is to verify Green's theorem. So one here. So the first exercise is again, it's just verify Green's theorem for F, force field F equal to, let's say, minus x squared y times x y squared, and D, let's say, is the disk. Disk x squared plus y squared, let's say, less or equal to 4. Okay. Number 2, same thing, a different region. Let's say you want to verify Green's theorem for F equals to x squared minus y, x plus y squared, and D is a rectangle bounded by the lines, say x equal to 0, x equal to 2, y equals to 0, and y equals to 1. Okay. And the last exercise. So in these two exercises, guys, where you have to verify Green's theorem, you can just follow the example I had here, right? In this example, we had so all we did was just to verify Green's theorem, right? We said sorry. So we had like two main steps. Where is it? Well, it's kind of it looks like it's too long, but it's just because I'm giving all the details here. But yeah, so first step we said is step 1, we have to evaluate this vector line integral along the boundary of D. So the problem is, the vector field F, capital F, is given. That's not a problem. The problem is to parameterize the boundary, right? So that's what I said here. We need to parameterize the boundary. And that's what I did here, right? And so the boundary of my D was like C1 union with C2. And then next, I try to parameterize C1 and C2. And once you parameterize the boundary, then you can evaluate your vector line integral. I'm sorry, I lost my voice, I guess. So yeah, we can evaluate this vector line integral, and because like in this case, the boundary is given by the union of two curves. Like we have this line y equals to x, and we have this parabola y equals to x squared. So I had to divide my vector line integral into the sum of two vector line integrals, right? Okay, so once you do that, then you have to evaluate, of course, the right side. So this is like the step number 2. you have to evaluate this double integral of the region D, right? So you know the region D, you can parameterize the region D. You can find bounds for D, and then that's not really bad. Like here in this example, D is a elementary region, so we can find the boundary for the bounds for D. And once you have the bounds, then it's just a straightforward computation, right? It's just a double integral. Anyway, so that's what you have to do, guys, in these two problems, 1 and 2. Third problem number 3. So in this problem number 3, we're going to use this remark I made about the as a consequence of the Green's theorem. So we said, as a consequence of Green's theorem, we can actually relate the area of your region D to this vector field. Okay, so you can just if you wanna compute the area of your for some region D, all you have to do is to evaluate this vector line integral along the boundary of D, right? Using this vector field F. Okay, so you need to use this vector field F. So exercise number 3 would be the following. So use Green's theorem to find the area between the ellipse x squared over 9 plus y squared over 4 equals to 1, and the circle x squared plus y squared equal to 25. Okay. So all I'm saying, guys, so the remark is, again, the remark you have to use is the following. So anyway, so if you, of course, if you want to try to sketch this this region D, so we have the circle, so here's 5 here, and I'm gonna need probably 3 here and 2 here. Anyway, so we have this circle, and you have this ellipse. All right, and you want to find the region, the area of this region D here. This is your D. Okay, and so what we are saying, guys, is that of course the boundary of this region D would be these two curves, this C1 here, right, and of course the ellipse C2. Okay, and so all I'm saying, guys, all you have to do here is to use the fact that so the area of D, which is by definition, 1 dx dy over D, that would be actually half of the vector line integral along the boundary, where F is equal to minus yx. Okay. Anyway, guys, I'll probably come back to this next time. It's already time. So I'm gonna stop here. So next time, what I'm gonna do, I'm gonna probably solve one of these problems, okay? Because it's in your homework, number 4, okay? So I'm gonna try to solve one of these problems, and then I'm gonna give you a different formulation of Green's theorem, which has like sort of there's a sort of a geometric interpretation of this Green's theorem, right? And then we're gonna come back to the chapter 7, right? So I'm gonna stop here, guys. Thank you very much, and I wish you, I hope you're gonna enjoy your spring break. So I'm gonna stop recording, I guess. All right.